Previously, we talked about how a capacitor and inductor behave at t equals 0 plus and t goes infinity to build up some intuition. So now let's use that intuition to just logic our way through how a circuit's behavior changes in the presence of a reactive load. So let's start by reviewing what actually happens if we have an open and a short circuit. And then we'll add the capacitor and the inductor in and draw the lines in between them. So to start out, in all these cases, we'll start with a source and we'll assume that it's impedance matched on the generator end. So let's start out by looking at a short circuit, and we'll also look at the open circuit. And then once we've looked at that, we'll also see what happens when we put in a capacitor and an inductor. So in this case, we'll look at the capacitor and the inductor. Now in this case, I said they're impedance matched on the generator end, so whatever happens, there's going to be a reflection and then it's going to reach steady state. The other thing to remember is by matching at the generator end, these two impedances are the same. So what's the initial voltage going in? What's the initial V plus? Think about it, it's the voltage divider, right? So V plus is going to be 1/2 VG in all of these situations. So that's something to keep in mind. So now we have the inductor. So CL, inductor on the load side. Now, in all four of these cases, we're going to look at the voltage at the generator side, or this is what we're also call Vin. So this Vin here, and we'll also look at VL. Let's start with the short. So when we start out, t equals 0, the wave's going to go in, and you're going to have 1/2 VG going in, right? And then it hits the short. What's the reflection coefficient of a short? It's -1, right? So at time 2t, the -1 wave comes back, and then it cancels the incoming wave, so you get 0 for the rest of the time. And that makes sense because we know that in the end, the voltage drop has to be 0 if you're shorted out. On the load side, we're going to see that basically nothing happens, right? The voltage comes in, but it immediately dies out because of the reflection coefficient of -1. Now let's look at the open circuit. So in the case of the open circuit, we're going to have the same 1/2 VG come in, but then it's going to bounce off the open circuit. What's the reflection coefficient for the open circuit? +1, right? So then the reflected wave comes back and you get another bump of 1/2 VG. So this takes you up to VG at time 2t when that reflected wave comes back, and that's going to be your final voltage. The load end is kind of similar, where you start out with nothing, but then at time equals t, it bumps up and it goes immediately to VG. Now let's see what happens in the case of a capacitor. So for a capacitor, on the generator side, you start out with your signal going in, your 1/2 VG. That's going to be the same in all cases. And then what happens? At 2t, the initial thing that happens when it sees this capacitor, it behaves as a short. And so the initial response is going to act like a short. So you see in the short, it goes down to 0. So in this case, it goes down to 0. But over the long term, this becomes an open circuit. So you expect that over the long term, it approaches the open circuit solution of Vg. And how does it get there? It will get there in an exponential shape. So that's how it's going to look like on the generator end. The load end, following the same logic, is going to start out with a short circuit solution, which is 0, but then over the long term, it's going to charge up and approach the open circuit solution, which is Vg. So let's take a look at the inductor using that same logic. Inductor starts out as a short circuit. So regardless of what happens, you're going to be at 1/2 Vg going in if you're matched at the generator. And then at 2t, the reflected wave comes back. What does a reflected wave start out looking like? Well, it starts out as the open circuit solution, right? The open circuit solution is going all the way up to Vg. So it starts out by jumping all the way up to Vg, but then over time it becomes a short circuit, so it will approach the short circuit solution, which is 0. So it's going to get there by decaying downwards. Applying that same logic to the load side, we see that at time equals t, the wave arrives and it starts out with the open circuit solution, which is going all the way up to Vg. But then over time, it's going to decay down to the short circuit solution, which is 0. So we have an open here and a short circuit solution here. And then in this case, it's the opposite, right? We evolve towards an open circuit solution, but start out with a short circuit solution. Now this same concept applies for circuits that have a resistive load in addition to the reactive load. So let's do a simple example as to what that would look like. Let's start by looking at a resistive, purely resistive scenario that we're familiar or more familiar with. So we're still going to impedance match it at the generator side. So the source impedance is Z0, the transmission line characteristic impedance is Z0, and in this case we're going to have a load, and we're going to set the load to be equal to 1/3 Z0. So in this case, the reflection coefficient is going to be equal to nu minus old over nu plus old, but in both cases they're a factor of Z0, so they're multiplied by Z0, so you can factor that out and cancel it, and you're going to be left with 1/3 minus 1 over 1/3 plus 1, which is going to be equal to -1/2. So when the wave comes back, it hits the load, -1/2 of the wave is going to reflect back. So let's see what that does to the input and the load voltage. So on the input side, it starts out the same up until 2t, because up until then you don't know what's on the other side, so it behaves the same. You have the voltage divider between the two Z0, so you have 1/2 Vg going in. But then when the reflected wave hits, you're going to have a minus half of that's going to come back, and that's going to cancel this out partially. So when the reflected wave comes back, you're going to reach a steady state, which is 1/4 of Vg. And that's exactly what you get when you saw the voltage divider between Z0 and ZL. On the load side, you start out with nothing, and then at time equals t, you have a voltage that goes up, and this is going to be 1/2 Vg. So now let's do the same thing, but let's add some reactive loads. So let's start with a shunt capacitor, same load, and then we're also going to look at when we hook that up to a series inductor. Again, the load is the same. It's going to be 1/3 Z0, so that gamma is going to be equal to -1/2 in both of these situations. So let's take a look and see what it's going to look like. Actually, before we do that, let's just try to reason what we expect to see, and then see if we can observe that result in simulation. So we start out behaving the way that we usually do, and we know that after a long time it's going to settle at 1/4 VG, right? Because that's what the overall long-term solution is going to be. When this becomes an open circuit, it's going to match up the solution that we had up here. So what happens initially? Well, initially it shorts out, right? So then we actually, at 2T, we go to the short circuit solution. Now remember what the short circuit solution is? Right, it's a reflection coefficient of -1, which cancels out the incoming wave. So you crater down to the bottom. And then over time, you slowly go back up. So this is like what we had before, except now notice that because of this resistor, it converges to what you would get if that reactive load wasn't there. Similarly, nothing happens until time t equals t, and then it converges to the same situation as what you had up here. So it's going to slowly charge up to 1/4 VG. And then let's look at the inductive load. Again, you start out at 1/4 VG until 2T when the reflective wave comes back, and eventually you're going to be at 1/4 VG. But what happens in between? Well, this starts out being an open circuit. So you actually start out with the open circuit solution, which is it jumping all the way up to VG, right? You have a wave that hits a reflection coefficient of 1, which doubles the input wave and brings it all the way up to VG, and then over time it slowly discharges back to 1/4 VG. Similarly over here, the time t equals t, you start out with the open circuit response, which is VG, and then it'll slowly discharge down to the 1/4 VG. That matches what we had before. So let's see if that actually happens in simulation. So over here, I have a really old program that was provided to me by Professor Morse Cohen. And I will provide this program for those of you that are taking this class to download so you can play around with it. So let's just, for kicks, let's just start by looking at what a pure capacitor load is going to be. So you set it up like that. The default is to have it match at the generator side. The input voltage is 1, and let's just see what happens. So you see this initial wave going in, speed it up a bit. Starts out with the short circuit response, and then progressively converges to the open circuit response, which is double what the incoming wave was. Similarly, let's try that with inductor. So you have your wave coming in, starts out with, and then it hits inductor, gets the open circuit response, so it jumps up to twice the size, but then it eventually goes to the short circuit solution. So now let's try the RC circuit situation we had before. We wanted this to be 1/3 of the characteristic impedance. So we'll do that. Do 16.666 and run it, and let's see what happens. So this goes in, starts out at this 0.5 amplitude here, bounces out, has a short circuit response, but now you see over time it stabilizes to half the value. Now let's try that with the series RL load. Gonna run it. It's traveling across, hits inductor, gets the open circuit response, and then slowly discharges back down. And then, as in the parallel RC example, it eventually steadies out at half the value of the original input wave. But as you can see, with a little bit of knowledge as to what the final solution is going to be and how the capacitor and the inductor behave right at the moment of impact versus you know how it behaves right when stuff starts happening, right when the wave hits it, and then you should be able to just at least intuitively draw the line, an exponential-like line, to the purely resistive load solution. So this is kind of the intuitive approach of how to reason how a reactive load behaves. And then separately, we'll also look at how to dive into the differential equations and come up with expressions for its behavior.